There's this really crazy idea out there that your thoughts could affect gravity. Maybe a thought of peace could make gravity work better. Now, before we get into this, we have to talk about the real science behind it. And for that, let's go back to school. When we were in physics class, we learned that everything has gravity. Gravity depends on the mass of the object and how far away it is. That's what we use to calculate gravity, and that's what this chalkboard here is doing. But what if this equation was wrong or incomplete? What if something else had to do with gravity? Well, it turns out that there are some physicists out there who have been thinking about exactly that. In fact, there's a researcher named Boko from Istanbul who believes that the equation for gravity needs a couple revisions. He thinks that gravity comes in two flavors. In today's episode, we're going to see what those flavors are and how they affect our understanding of the universe. This is the second law of Boko. Now, if you've been following for any amount of time, you probably know that many physicists are trying to do the seemingly impossible, finding a theory of gravity that unifies the very small and the very large. You see, Einstein's general relativity describes how gravity works for planets and stars and galaxies. But when it comes to the realm of atoms and photons, that job goes to quantum mechanics. And these two theories don't get along very well. They say completely different things about how the universe works. So a lot of physicists would love it if we could find one theory that explains both the very small and the very big. But while many of those physicists are looking for new types of particles or forces, Boko's theory is a bit different. His equations look similar to Einstein's. That's because he isn't rejecting general relativity. Instead, he's extending it. Boko says that general relativity misses two key ingredients, two things that can warp spacetime just like mass does, but which aren't mass. Those two things are order and consciousness. Let's take a look at the math. First, we need to talk about the Milky Way. The Earth goes around the center of the galaxy once every 225 million years. And since the Earth isn't the only thing orbiting the center of the galaxy, the Milky Way has what physicists call a massive rotation. Now, this rotation generates another kind of rotation, a rotation in space itself. It's called a vortex. We're used to thinking of vortices as being swirls of water or smoke. But this one is different because it's invisible and it's made of quantum mechanics. The vortex of space is called the galactic quantum centrifugal field, or FQCF. According to Boko, the FQCF is the main contributor to the gravitational field outside of the galactic disk. So the first term in his equation for gravity is the galactic quantum centrifugal field. Next, let's turn our attention to Earth. All life on Earth, whether it's people or plants or bacteria, has what Boko calls bioenergetic dynamic gravity, G-Earth. That's the second term in his equation. This field is created by all the living things on the planet and by the buildings and machines we construct. In other words, it comes from the order we impose on the world. According to Boko, G_Earth is significant inside of Earth's atmosphere, but gets weaker the farther away we go. So now we have an equation with two G's. Let's see how it works. If you want to calculate gravity with Boko's equation, you still need to know the masses of the objects involved. But now you also need to know their distance from the galaxy's center and the amount of order they contain. The more massive an object, the stronger its gravity. But according to Boko, the same goes for the more ordered. Now, at this point, you might be wondering why we haven't noticed these extra effects. After all, if G_Earth gets weaker with distance, shouldn't it be easy to notice when you leave Earth's atmosphere? To answer that question, we need to talk about the constant Gi. This constant appears in Newton's gravitational equation, and it tells us how strong gravity is. More specifically, it tells us how strong gravity is compared to electromagnetism. Without this constant, we wouldn't be able to sit on chairs or walk on the street. Gravity would be too weak. But maybe that's not a good thing. According to Boko, the reason we have unnoticed these extra effects of gravity is that the value of G is unactually constant. It changes depending on how much the objects involved have influenced their surroundings. For example, Earth's influence on the Moon makes the Moon slightly larger than it would be otherwise, so the value of G is a little bigger near the Moon than it is far away from Earth. Similarly, if you were to measure the value of G on Earth's surface, it would be slightly larger than the accepted value. And that's because most of Earth's mass is in the center of the planet. So the stuff on the surface is closer to more mass and therefore feels stronger gravity. And that's why, according to Boko, we haven't noticed these extra effects of gravity. They're drowned out by the large mass of Earth. Now, it's worth pointing out that this idea hasn't been tested. And to be fair, it's extremely hard to tease apart the effects of order and consciousness from the effects of mass. But that doesn't mean that the idea is wrong. It's just one more piece of the puzzle in the quest to unify gravity. Now, if you'll excuse me, I have a sudden urge to start meditating. Okay, so this idea seems pretty wild. A thought of peace could change gravity. But maybe it's not as far out as you think. In fact, there's another physicist who thinks something similar. This is Jagadish Shukla. He thinks that Earth's gravity is affected by the planet's weather. When it's stormy, gravity is weaker, and when it's calm, gravity is stronger. Now this sounds pretty crazy, but we already know that the weather affects gravity. Take a look at this map. The blue areas show where Earth's gravity is slightly stronger, and the red areas show where it's slightly weaker. And this is due to differences in elevation and temperature. For example, in mountainous regions like the Himalayas, the air is thinner because it's less dense, and thinner air means weaker gravity. So we already know that the weather affects gravity, but what Shukla has done is come up with a way to quantify it. He wants to be able to take any weather map and plug it into Newton's equation for gravity. Now, this has never been done before, and just like Boko's ideas, Shukla's ideas haven't been tested. But that doesn't mean they're wrong. Both of these physicists are saying essentially the same thing. The difference is that Boko ties gravity to the amount of order in the universe, whereas Shukla ties gravity to the amount of chaos. Now, at this point, we should talk about the elephant in the room. Both of these ideas hinge on the idea that humans have free will. Remember, Boko said that G_Earth is due to the bioenergetic dynamic gravity of living things, and that includes people. And Shukla's idea relies on the idea that people can control the weather. But do we have free will? I think we can safely say that we can choose what we do. We can choose what we wear, or what we eat, or who we befriend. But is that all there is to free will? Is it just the illusion of choice? Or does the choice actually matter? Does it affect the world? Some philosophers say no. They say that all choices are predetermined, and the illusion of choice simply comes from our ignorance of the complex web of cause and effect. But others say yes, the choice matters. They say that humans have a kind of energy that can move the world, and that brings us back to gravity. What if the difference between these two views of free will could be measured by how well gravity works? If we're just puppets of the universe, then G_Earth should always stay the same. But if our choices actually matter, then G_Earth should fluctuate based on the amount of order and chaos in the universe. So the next time you feel like gravity is holding you down, remember that it might also be connecting you to the heart of the cosmos. Thanks for watching this episode. I hope you learned something that inspires you to keep questioning the universe. And if you want to learn more about how the universe works, we have another channel that covers physics and math. And we have a whole playlist of videos that you can watch right here.